Hi, how are things?
Good, how are you?
I'm hanging in there. Okay. Okay, I think we should get started then. Let's get this show on the road. Get the camera in the right place. There we go. Well, today we're going to look at section 11.4, which is the comparison tests. There's two of them. One of them is called the comparison test, and the second one's called the limit comparison tests. So let's look at the first one. Right, what this says is essentially the following. Suppose we have a test, suppose we have a series, I should say. So suppose we have a series, sigma bn, that we know converges. We can use this known series, the one that's converging, and we can use it to prove that another series is also converging. And what it says is the following. If an is less than or equal to bn for all n, then the series sigma an will also converge. So in layman's terms, if we have a series that's made up of terms that are smaller than a series that converges, because you're smaller than a series that converges, you must also converge. Seems reasonable. And there are two parts to this test. The other one says, suppose that we have a series, we'll call it Bn, that we know diverges. If our series, the sigma an one, if an is always greater than or equal to the term bn for all values of n, then we can conclude that the series sigma an will also diverge. Okay, that's essentially it. And the application of it may be a little bit trickier. So these guys, these sigma bn's that we know converge, or the sigma bn's that we know diverge, are almost always going to be P series and geometric series. Let's do an example. Suppose we want to see whether that series sigma squared sine sigma of the sine squared of n over n cubed, and we'd like to know if it converges or does it diverge. First step we need to do is find an appropriate comparison series, sigma bn. Right, now if you look at sine squared n over n cubed, and you wanted to find a p series, because that's typically a p series, would it seem reasonable that a good choice would be 1 over n cubed? Can you see that's not random? Can you understand why I would be choosing this when you look at that guy? Our comparison series must behave in a similar fashion to this one. So I've decided to use this one. N cubed in the bottom and a number on the top. I need a number on the top and I need some power of n on the bottom. Step 2, do the comparison. So here we go. Sine squared over n cubed. Would you agree that sine, although it takes many values, the sine of n always takes a value less than or equal to 1? So sine squared n over n cubed would be less than or equal to 1 cubed. Would you agree with that? So that's my an, and I'm proving it's less than the bn. And I almost forgot something. Do you see my comparison series? Do you recognize this guy as a p series? And that p is equal to 3. So this guy converges. Now, haven't I just shown that my series is less than or equal to this guy? So according to this, if you are less than or equal to something that converges, then so do you. So you would finish with, so this fella converges by comparison test, I guess. Okay, try another one. Suppose I'm interested in e to the 1 over n, right? Suppose I was interested in that series. Who should I compare that guy to? What p series should I compare this fella to? Any ideas?
I guess E over N.
Well, it's not that far away. Simplify it just a little bit more. Instead of E over N. 1 over N. Agreed? It's a little bit simpler. Now, my comparison series is this fella. This fella is a p series. P is equal to 1, so this diverges. Isn't e to the power of 1 over n greater than or equal to 1 over n? Right, the bottoms are the same. And can you just trust me that if you plug in 1, 2, 3, 42, this guy is a little bit bigger than 1 every single time. So if you are, your guy is bigger than someone that diverges, then you diverge. By the comparison test. So you find the series that it behaves like. If the series it behaves like is a diverger, you have to prove that the original is bigger than it. And if the series that you find is a converger, you have to prove it the other way round, right? That your guy, right, the original, is less than that fellow. And those are the two good situations that you're always trying to find. Now, why I didn't pick E? Well, E over N isn't less than this. It's actually bigger than this, and that's no good to us. Because if you're bigger than something that converges, or if you're less than something that diverges, you can't make any conclusions about that. Right? Couldn't you be something that's less than a diverger and still diverge as well? Couldn't you be bigger than a converge and still converge? So we have to be less than something that converges or bigger than something that we know diverges. Any questions? Okay, I'm going to show you some examples from the homework and see, oops, I don't know what we're looking at here. I'll try that again. Right, are you looking at questions 1 and 2 from the homework? Is that the screen you're saying? Should be question 2 right now. Make it a bit bigger. Yeah, you see it now? Right, now, in every single one of these questions, at least the ones I'm going to show you, we're going to do the comparison test to it. So the first thing is we have to figure out what does the guy behave like, and then prove, you know, that you're bigger than that guy or less, depending on what you're looking for. Okay. Now, if you're looking at question 2, wouldn't you call the top guy n and the bottom guy n square root of n? Right, can you see that would be your comparison? Now, if you did that, wouldn't there be a little bit cancelling, and this would end up being 1 over the square root of n? Is 1 over the square root of n a converge or a diverge series? 1 over the square root of n, does it converge or diverge?
Converges.
Okay, let's check it out. See what we get. Right, that's the original, right, with the sigma beside it, but we'll just focus on the original. Now, I'm saying that that behaves like this guy. And then after tidying it up, it looks like this guy. Now, if you put it inside sigma, the question I was asking, does this converge or diverge? Maybe what I should have said is, if you write it like this guy, does it converge or diverge? Do you see a P series?
Oh, so why is it that there's just a n there instead of n plus 1?
Oh, because I am trying to take this guy and find out what he behaves like. So when I say what he behaves like, I try and take the original one, right, and simplify it a little bit, right, trying to turn it into something that can be written as a p-series or a geometric series. That's the two guys we tend to compare. Now, I can't do anything if I leave it as n plus 1 over n root n. I mean, nothing obvious. But in the big scheme of things, if you take a billion, won't a billion and one and a billion behave pretty much the same way? So in a simplification, right, a rounding off, a comparison, it's okay to do that. That makes sense?
Okay, so
Right.
this is using the comparison test.
This is us doing a comparison test. So the first step is to find something to compare it with. So that's a bit messy, so I simplified it. Right? I pretended that the one really doesn't matter in, you know, when you're talking very large values, and it doesn't. And then you cancel the ends and you got this guy. Now, this guy here is the comparison one, the fella that we call sigma bn. And my question was, does this converge or diverge? It's a p series and p equals a half.
Oh yeah, now it diverges.
Now
But
you know
why couldn't you do the p test with that?
Well, what with the original?
Yeah.
How could you? You can't. The p-test needs it to be written as 1 over something or 5 over something, not n plus 1 over something.
Okay.
So this particular one, right, this diverges. Now, if you take this guy, would you agree that he is bigger than that guy? Right? Is the original bigger than this fellow? Yes. Can you see if the bottoms are the same? Bigger than this. N plus 1 is bigger than n. So what do we know? We know that this fella, right, is bigger than that guy. Oh, I just realized that is the wrong way around. Don't we need to prove that? Oh, I'm okay. It's the right way around. That's the original. That's the simple. Yeah, it's bigger. You are bigger than something that diverges. So the original series also diverges. Our goal is to take a series we don't know whether it converges or not, find something it behaves like, and then prove that our guy behaves like this guy. So in this case, this guy gets replaced by this simple fella, who's a p series that we know diverges. Then I need to prove that my guy, the original, is bigger than him. If you're bigger than something that diverges, you diverge. And that's us finished. Okay, here's the next one then. Suppose I give you this fella. And I would like to know, does this converge or not? Tell me a p series that is similar looking to that. Now, if you're going to be a p series, you need one on the top. What p series is that guy going to be this, to be at least similar to? It doesn't need to be the same as, but similar. Okay, let's look at how we do it then. You make the top one. What do you do with the bottom? Change it into k cubed, make it sine k, e to the k, tk. And I never did any of those. What do you do? And do something pretty straightforward. Don't do anything clever. What does happen to that guy?
Square it.
Yeah, that's all. Okay. What I'm going to do now then, because it seems to me that this idea of simplifying you find it a bit challenging, is let's just do some simplifications and not do anything else. Just get used to simplifying. I want to simplify n cubed over 4, n cubed plus 4 over 4. I want to simplify sine squared k over square root of k. I want to simplify e to the 1k over n to the 4, well, it'll be a k then, k to the 4. I'd like to simplify log k over n squared. I'd like to simplify inverse tan of n. I keep on putting k's and n's, so let's make them the same way. That guy over n cubed. Each one of these is going to be turned into a p-series. We just have to figure out what the appropriate p-series is. Right, let's look at this one. N cubed plus 4 on the top, n to the 4 on the bottom. Picking n cubed on the top and n to the 4 on the bottom. There's our simplification guy, sigma 1 over n. You want to do a sine squared k over square root of k. The worst thing a sine can be is 1. So you get 1 over that guy, which is basically 1 over a k to the half. P-series. E to the 1 over k over n to the 4. K to the 4. 1. That's a p-series. Log n over n squared. 1 over n squared. There's your p-series. Inverse tan of n over n cubed. Right, the inverse tan, the biggest and best value it can ever be is pi upon 2 over n cubed. Or 1 over n cubed. Do you see where we're going with this? That when you try and find the simplified version of it, you're really trying to find out what p-series is it similar to. So it has to be 1 over some power of n. And the power of n isn't random. The power of n has to be connected to the original expression. Now, the one that we just finished doing was this one. So this guy behaves like 1 over k. 1 over k is a p-series. It's a p-series where p equals 1. That means it diverges. Now you write down the original. And is it true that the original is bigger than or equal to 1 over k? And the answer is, in this case, that is true. Because won't log of k be bigger than 1 once k is 1, 2, 3, 4, and so on? If you can prove that your guy is bigger than a diverger, right, your guy is bigger than a diverger, then the original series also diverges. And that's that's the process to showing that a series that looks like this converges or not.
So what are you doing when you simplify? Is it just like taking the limit to infinity?
When I simplify it, what I am doing is I'm not making any limits here. No, that wouldn't be a good way to look at it. What I'm trying to do is think of what this function's in essence, what its behavior is. So when I look at an expression like this, I'm saying to myself, well, okay, it's got a number on the top that keeps changing, but the k on the bottom's pretty much k. This guy here should behave like him, right? The bottoms are the same. Okay, this guy is a little bit bigger than him, but that's okay, because I want my guy to be bigger than him. because this guy diverges. And if my guy is bigger than him, so I diverge.
Okay. I understand.
So you're looking at an expression, you're trying to say, okay, who does he behave like? And then you would do that as your comparison. So we've done E1 over there, and I've done that one. Okay, let's move. Well, no, we don't need to do that one. Right. Okay, let's do this one. This is a version of question 13. And we're being asked to find and to prove that this guy does it converge or diverge? So I'm going to find something that's similar mathematically in behavior to this guy. I don't do anything with him. And then I look at the inverse tan, right? Now, if you know anything about the inverse tan function, it just gives you an angle, right? That is equal to, you know, if that was 12, it would be what angle has a tangent to 12. If it was 50, it would be what angle has a tangent to 50. The worst case scenario for this function is pi upon 2. Right, the inverse tan of infinity would be pi upon 2. So I don't want fractions, although I could get away with it. I'm just going to call it that guy. So my original, the function I'm trying to find out, does this guy converge or not, behaves like this guy. And if you stick sigmas in front of them, if that helps, do you recognize a p-series? The p is 1.2. If you have a p-series and the p-value is 1.2, does it converge or does it diverge?
Converges. It's greater than 1.
Yeah. Now, to kind of finish off the proof, we just need to say that our guy is bigger than that guy, right? And actually, do it the other way around. Our guy is less than that guy. And so you converge. And that's the comparison test. That's number 1. Any questions about the comparison test before we look at the second kind, which is called the limit comparison test?
I mean, do you have any other problems you can go over on that one?
Let's do a quick scan. There's a mixture of both kinds of questions, so I'm going to just go through each one quickly and tell you which method we would use. And I keep doing this because I can't see on my screen because it's been weird today. There, you should be looking at question 1 right now. Question 1 is just the test, and you decide how to write it down. Right, question 2 is a comparison test, and we did one like it. Question 3 is a comparison test, and we did one like it. Question 4 is not a comparison test. And the reason I cannot use a comparison test here, can you see that there's more than one term on the top and the bottom? If you want to do a comparison test, the bottom has to be simple, right? It has to look like that. Right? It has to be simple, right? That's not good. That's not a comparison test. Neither is that. This one is a comparison test, and we did it. That one there is not a comparison test. Now look at it. Neither's this one. Neither's this one. Not a comparison test. We did this one. It is a comparison test. Not a comparison test. Not a comparison test.
You did those today?
Not yet. The ones I've said we've done today. But 15 is not a comparison test. If it's not a comparison test, I haven't done it yet. 16 is not a comparison test, neither 17, 18, 19, all the other ones. Okay, so we have done all the ones where the comparison test is the way to go. Right, so we've done every single example that can do that. So now we have to look at how do you do tests, right? Guys that look like question 4, guys that look like question 5, where you aren't able to do the comparison test, right? They're too complicated. They don't have an n squared in the bottom. You can't easily figure out what the thing is. So that particular situation is called the limit comparison test. So that's what we need to use. So I'm going to do some math before we even go near this guy. If I asked you to find the limit as n tends to infinity of n cubed plus 2n squared minus 5 over n to the 4 plus 2n minus 1, right? For example. We are going to be doing a lot of questions that look like this. We're going to be finding the limit as n tends to infinity of essentially ugly fractions. There are 2 methods that you can use to solve this limit. The first method is you can divide the top and the bottom by the same power of n. In this case, I'm choosing n to the 4. The second method that you can use, which is equally valid and does work, what is the second method? First method, you divide the top and bottom by n squared or n cubed, whatever it takes. What's the second method?
L'Hopital.
And so you would do L'Hopital, right? So if I return back to this one, if you divide everybody by n to the 4, you got 1 over n plus 2 over n squared, take away 5 over n to the 4. And on the bottom, you got a 1 plus 2 over n cubed minus 1 over n to the 4. And then you do brute force. So you got 1 over infinity plus 2 over infinity squared, take away 5 over infinity to the 4. And then you have a 1, 2 over infinity, take away 1 over infinity to the 4. 0, 0, 0. 1 plus 0, 0. Answer is 0. So in this case, the limit is 0. If you did L'Hopital instead, you would go something like this. You differentiate the top. You get that. Then you try and put an infinity in, but it doesn't work. So you do L'Hopital a second time. And you get 6n plus 4 over 6n squared. That should be 12 actually, 12n squared. And it still doesn't work. So you do L'Hopital one last time. And you get 6 over 24n. And then you put in infinity. And 6 over 24 infinities is still infinity. And so the answer is 0. Do you see that the top method tends to be quicker than L'Hopital if you have powers that are reasonably big, right? N cubes, n to the 4s, and so on. Now, as long as the powers are relatively small, right, quadratics, this method will be just as quick, if not even quicker than that one. So that's your two techniques. Divide top and bottom by a power of n, or do L'Hopital. So that's a skill that we're going to be using. Here's another skill we're going to be using. We're going to simplify an expression into its basic structure. And we've already done some of this today. We're just going to do more complicated versions. So if I add n cubed take away 2n plus 1, and I have 4n squared, 4n to the 12 minus n squared, right? And I wanted to simplify this into its basic structure. We use the OC symbol, which doesn't mean it's equal to it. It means more, it behaves like it, right? It's in a similar kind of structure. And you only take the biggest power from the top and the biggest power from the bottom. And you got that guy. And then we simplify it so that it's only a single power of n when you're finished. You see how we can take from here to here? Now, what that tells me is that this, if you put a sigma around it, this series behaves like that series. And what do we know about that series? We know it's a P series and we know it converges. So I can tell you right now that that is going to converge only because of this process. But I haven't proved it. I know it's going to converge, but I have to prove it. And the proof part is what the limit comparison test does. This is part of the process. How do you simplify an expression into its basic structure? So here's another one. N to the 4 minus n over n to the 6 plus n. Okay, what would be the simplified numerator in this case? What should I write down?
No, the fourth.
Okay,
1 over n squared.
and there you go. That guy is basic structure of what this looks like. So if you stick a sigma around that, can you see that this is going to converge? But we have to prove it. Why do I know it converges? Because 1 over n squared is a P series. The P value is bigger than 1, so I know it's going to converge. Now you can also do it with these guys. When it was powers like this, you pick the biggest power to go on the top, you put the biggest power on the bottom, right? These are different situations, but the rule still applies. You don't put 7 to the power of n on the top. You don't put 12 to the power of n. You don't do any calculations. What you do is pick one of these two guys. And the guy you should pick is the most important one. And what is the most important one? 3 to the n or 4 to the n? Well, the one that's the biggest is the most important. So which is it?
Or then.
Okay. Now, if you're doing the guy in the bottom, the same argument, would you agree that 7 to the n is the bigger of the two? So this guy behaves like this fella. Now, this isn't quite the way I need it to be written, but I am allowed to do that. Do you see the R value now is 4/7? Can you see that that's going to converge, right? This guy is going to converge. Right? Remember a geometric series, if the R value is less than 1, it converges. That's why I know. Suppose you get a guy that looks like that. Only one of those two belongs on the top. And the one that belongs on the top is the bigger. N squared or 2 to the n. Well, think of a number like a million. A million squared or 2 to the power of a million. Who's going to win that battle? Who's going to be bigger? Well, just do 10. 10 squared or 2 to the power of 10. Who's bigger? Ten squared is 100. 2 to the power of 10 is 1024. Powers always beat, right? 2 to the powers always beat n squared or n cubed, actually any of them. So on the bottom, 3 to the n would win. That can be written like that. I now have a geometric series. Yep, that one converges as well. Are we getting better at understanding how you take the original and find out what it behaves like? Its basic structure series. That skill is something you really need to be able to prove that all of these tests converge or diverge, whatever they end up being. And that test is called the limit comparison test. So let's show you how it works. If you have a comparison series Bn that we know converges, and the limit as n tends to infinity of the original over that guy is equal to L, where L is not equal to infinity, we know that the original series AN will also converge. So if you can find a sigma Bn that converges, and the limit of this fraction is a number that's not infinity, then we know that your original will converge. Now, if this series that we know diverges, and the limit as n tends to infinity of AN over Bn equals L, where L is not 0, then the series, the original one, diverges. Okay, that's the test. There are two versions. The top one is what you would use if you're trying to prove something converges, and the one underneath it is the test that you use, the version of the test you use when you want to prove that it diverges. So our first example is number 4. So we have this fella. Step 1, find the comparison series. Find Bn. Okay, let's see how that works. N squared plus n plus 1 over n to the 4 plus n squared. It behaves like n squared and n to the 4, which is 1 over n squared. Okay, I found my sigma bn. It's sigma 1 over n squared. What do you know about 1 over n squared? Does it converge or diverge?
Converges.
Correct. And the reason it does that, it's a p series, p equals 2, which is greater than 1, so it converges. Okay, so we are on number 1 up here, the top one. What we now have to do is find the limit of an over bn, get a number, and as long as that number's not infinity, we know that our original will also converge. So here goes. The limit as n tends to infinity of the original divided by the comparison. It's going to be the limit as n tends to infinity. And you get some really ugly expressions out of this. An is all of that. So it's n squared plus n add 1 over n to the 4 plus n squared, right? Just a single expression. On the bottom, Pn, which is that guy. Nobody in their right mind would want to try and evaluate that limit the way it's written. So what I'm going to do next is simplify it. I have a fraction where the top, the numerator, and the denominator are themselves fractions. So I can change this into the guy on the top that's this guy, divided by the guy in the bottom. Normally you don't write this line. Normally you jump right into the one I'm about to put down here. Isn't dividing by 1 over n squared the same thing as multiplying by n squared over 1? So normally you should be able to jump from this ugly thing to this slightly nicer fraction. The next step, is pretty standard, is all of this gets multiplied by n squared. So I get n to the 4 plus n cubed plus n squared. And on the bottom, I get n to the 4 plus n squared. Okay, so the limit is n tends to infinity of the original divided by the comparison guy ends up being this fella. Okay, how are we going to find that limit with the least amount of work? What technique shall I use?
Divide by n to the 4th.
Seems reasonable. So divide top and bottom by n to the 4. Now I could do L'Hopital, but wouldn't I probably have to do it about 3 or 4 times before I got anywhere, which is a lot of work. So it's now going to be the limit as n tends to infinity of 1. Divide that guy, you get 1 over n. Divide that guy, you get 1 over n squared. And then on the bottom, you're going to get 1 plus 1 over n squared. And then I can do brute force. 1 plus 1 over infinity plus 1 over infinity squared. And on the bottom, 1 plus 1 over infinity squared, which is 1 plus 0 plus another 0. And on the bottom, 1 plus 0. And the answer is 1. Is our limit a number that isn't infinite? Yes, our limit is the number 1. And so we can conclude that the original series now converges. So that series converges by the limit comparison test. If you think about it, there is a kind of logic to this process, isn't there? Right? You take the original and you find out some simpler version of itself. Something that you can find, is it convergent or divergent, very easily. Most of the time it's a p-series, sometimes it'll be a geometric. Once you've identified the comparison series and you've found out, in this case, it converges, you then move on to phase 2, which is find the limit of an, the original, divided by the comparison. Do the algebra to make it look pretty. Plug in infinity with brute force and get a limit. If the limit is a number that's not infinite, your series converges, in this case. Any questions about that one? We good? Okay. Let's try an uglier one. Let's do 6 or 7. What shall I do? I'll do 6. Sigma n equals 1 to infinity. 2 plus 3n over 3 plus n squared cubed. Whoa, that's going to be a good one. That fella there, 3 plus n squared cubed. I'm going to have to find out what that guy is. Three is 27. You're going to get 3 times that guy squared, so you're going to get well, 133. You're going to get 9. Oh, you're going to get 27 times n. You're going to get 1, 3. Well, that's an n squared. You're going to get 1, 3, another 3. You're going to get 9 into the 4s. And you're going to get an n to the 6. And you just have to trust me, but you can FOIL it out. Okay. So we have a really ugly polynomial, which I'm going to write from biggest to smallest. Okay, what should I write down for the top line? What should go here?
Again.
Okay, seems reasonable. Would you agree that n to the 6 goes in the bottom? Now, if I tidy that up, you get 3n to the 5, don't you? Right, one of the n's cancel. And nothing wrong in using that, but I tend to use the 1 over version. Just, to me, the math is easier, that's all. Nothing wrong with that one, but I like to use this one. Would you agree that's a p series, p equals 5, so it converges? Right, 1 over n to the 5 is a p series. P equals 5, which is definitely bigger than 1, so it converges. So now we're looking at the top situation again. The limit is n tends to infinity of an over bn, which is this ugly fraction do this version here. Divided by this guy. Well, if you want to divide by 1 over n to the 5, it's the same thing as multiplying by n over 5 over 1. So that saves a line of work. So it now becomes the limit as n tends to infinity of 2n to the 5 plus 3n to the 6 over all of these guys. Okay. Polynomial, biggest power is 6. Polynomial, biggest power is 6. Divide top and bottom by n to the 6 is a good strategy, rather than doing L'Hopital lots of times. Two n to the 11, sorry, all the way around. 2 over n plus 3. 1 plus n over n squared, 27 over n to the 4, and 27 over n to the 6. Brute force now. 2 over infinity, I had 3 on the top. A 1 plus 9 over infinity squared, 27 over infinity to the 4, 27 over infinity to the 6. You get 0 plus 3 on the top, and 1 plus lots of zeros on the bottom. And the answer is 3. The limit of this ratio is a number that is not infinity. So our series converges. I could have had a good guess right there that this was going to converge. The reason we're doing all of this is a proof that it converges. You can't just say, oh, well, I can tell it converges, even although 99 times out of 100, you're going to be right. The whole idea here is we're trying to formally prove something. That's a little bit different. Apart from the fact that is one ugly expression when you FOIL it out, is there anything else here? Okay. Let's try a really weird one. Sigma 9 over n factorial. Now, if I write this down in its kind of full format, it's 1 times 2 times 3 times n plus 1. Okay, so I need to find someone to compare him against. And all bets are off. This is a unique situation. I have 9 on the top, and I have 1 times 2 times 3 times n plus 1. And I'm going to do this in 2 stages. I can get away with only using the last 2 terms. And then I can do that guy. And then I can do 1 over n squared. So I am saying that this guy behaves like a 9 over n squared. Now, I could have done, you know, I'll actually got those back to front. It's n minus 1 times n, which gets me n squared, which gets me 1 over n squared. I could have done three terms, right? I could have said n minus 2, n minus 1, n, and made it like n cubed, which would be okay, but it's just more work than I need. This is a p-series. And since p is equal to 2 and that's greater than 1, it converges. So I just need to take this guy, who's the original, and this guy, who is the comparison, and find out what their limit as n tends to infinity is.
Where'd the n minus 1 come from?
Oh, when you do a factorial, like n factorial, if you write it out in full, it's 1 times 2 times 3 times 4, and then you would finish on n. But the guy that would just before that would be called n minus 1, and I use those two guys. I just figured out I don't need to use all of them. The last two will do the job, so I did. Is that okay?
Well, you have at the top, you have n plus 1.
Yeah, I know that, but I fixed it.
Oh, so
Yeah.
okay. I'm sorry.
No, I should have rubbed that out. There. So this guy here should also be n minus 1 times n. Okay. Right, we have an, which is 9 over n factorial, divided by that guy. So that becomes the limit as n tends to infinity of 9 over n factorial times n squared over 1. So I now have 9n squared over n factorial. We did, God, when was it? It might have been Monday of last week. If not, it was the week before. When you are doing the limits as n tends to infinity of things like this, there's a little trick, relative growth rate. You remember that term? Relative growth rate. Isn't n factorial, the bottom here, much bigger than the top guy? You remember doing those? To remind you, the relative growth rate. The biggest thing in the universe is n to the n. That gets big really quickly. The next one is n factorial. That gets big really quickly, but not as quick as that. Then you have things like 2 to the n. Then you have things like n cubed. Right. Then you have things like square root of n. Then you have the slowest of the slow, which is log n. So this is called the relative growth rate. And they get bigger in that direction. So the biggest one is in the bottom. So the limit of those two is going to be 0. If the bigger one was on top, wouldn't the limit be infinity? So when you do a relative growth rate, whichever of the two is the bigger from this list, whatever is the bigger, always wins the battle. And so we get a limit of 0. And is the limit of an over bn a number? As long as that number's not infinity, you've got a you've got a converger. So we can now say that that guy converges. Any questions?
Tons.
Tons? Well, start me off with one. There's a lot of algebra going on here and a lot of little things that pop up that we have talked about, but maybe not as much as we should. So let me talk through the next question. because it's very similar to the one that we just did. Do you see this guy with the 5n factorial at the top and the n to the n in the bottom? That's going to converge. Right. And if you want to know who he behaves like, you can make him behave like a 1 over n squared. And the reason for that is that isn't n to the n, n times n times n times n times n, whereas n factorial is 1 times 2 times 3 times 4. So if you only look at the last 2 terms or the last 3 terms, you can make it happen. So we're now going to continue with the limit comparison test. See if we can figure out the next one. Okay, we need to find out who he behaves like. We then have to find the limit of the ratio and prove that it's a number. Okay. This one's a little bit more straightforward than the last couple. Top guy, don't have a choice. Bottom guy, not much of a choice. Tidy it up. And I don't like 3, so I just use the basics. This guy here behaves like a 1 over n squared. Does that make this guy a converger?
It sure does.
Sure does. So we have a p series. We have a p equals 2, so it converges. What we need to do now to kind of finalize that proof is show that this ratio is a number that's not infinite. So the original is this guy, divided by the comparison guy. We've done about 3 or 4 of these guys, so top fraction gets multiplied by the reciprocal of the bottom fraction. Multiply all the top together. Did I do that right? There we go, that's a cube. 3n cubed. It's a 2 plus 2. Okay, we're at this stage here. We need to find out what this is equal to. I could use L'Hopital on this one. Let's do that because I haven't done L'Hopital in a while. It would be the limit as n tends to infinity. If you differentiate the top, you get that. If you differentiate the bottom, you get that. If you cancel these down and simplify, you get a limit of a third. Is that limit not infinity? Yep. So this guy converges. By the limit comparison test. You're meant to write down these things here. These aren't just notes. These are part of the solution. You have to tell people why you know that converger, and you have to explain which test you're using and why does this work. I think we should show you a diverger then. This one I know diverges. So let's prove it.
So what if for the bottom one, if L did not equal 0, does that mean it would converge?
This bottom one, if I
Yeah.
I'm going to take this guy, and I'm going to prove that the limit is a number, and that limit is not 0. Right, now, if you end up wanting to prove something converges, but this limit here ends up being infinity, it means you screwed up on your BN, right? You didn't get a good comparison series.
Okay.
This one here I'm going to do. In this case, I don't want 0 to be the answer. If I got 0 as an answer, that would essentially mean that I chose a bad BN again, right? I mean, I could just look at it and say, oh, that series behaves like 1 over n cubed. And it doesn't even vaguely behave like 1 over n cubed, right? So that's to catch you. So if you try and use the wrong comparison, right, one of these horrible situations will happen, right? Infinity or 0 in this case. So here is the original. The top is n cubed, and the bottom is 2n to the 4, which I can simplify as 1 over 2n, which I like to call 1 over n. I don't like multiples floating about. They just get in the way of the question. Are we good so far that this behaves like a 1 over n? Now, that fella is a p-series. The p-value is 1, so I know it diverges. Let's continue with the proof then. The limit as n tends to infinity of the original divided by the comparison. It's the limit as n tends to infinity of n cubed over that guy divided by that guy. So it's a limit of this fella times the reciprocal, and it's now the limit as n tends to infinity of that guy. How are we doing? Is that kind of standard now? There is a kind of flow to these questions. What method shall I use to find this limit? What method?
Divided by n4.
Okay, that works. Also L'Hopital if you feel like it. So it's going to be the limit as n tends to infinity of 1 over 2 take away 1 over n to the 4. That's 1 over 2 take away 1 over infinity, 1 over 2. Did we get a limit L that wasn't 0? Yes, we did. So our series diverges. So that guy there diverges by the limit comparison test. Excuse me. Any questions? Hopefully not as many as there was a little. Excuse me. Asthma's not fun. Okay, any questions?
So in that last one, you dealt with if the sum of B and N that we know diverges, and the limit of A of N divided by B of N equal to L, it didn't equal 0. And that's why you
Correct.
said the series diverges.
Correct. As long as this isn't 0, it diverges. Right? And in the previous one, as long as it's not, as long as it's not infinity, right, it'll converge. So you notice there's a slight difference here. This limit has to be a number that's not infinity if you're comparing it with a converging series. And this ratio has to be equal to a limit that's not 0 if you're comparing it to a divergent series. So they're almost identical, apart from that.
I guess it really kind of depends on your P series, right? Which one of those you use.
That's right. Once you find how it behaves, right? Once you take the original and you break it apart into its essence, that's when you decide. So, for instance, this is 14. Right now, I'm making no commitment to whether that converges or diverges, right? I won't know yet until I've done the comparison part. Right, so you write down the biggest guy on the top, which is simply 3 root n, and on the bottom you've got an n. That simplifies down to 3 over the square root of n, which I will call 1 over n to the half. Can you see the P series that we're going to use now? That guy. And that guy is a P series. Its P is a half, which is less than 1. So does that make that a converge or a diverge?
It's a diverge.
Okay. So I know that when I do the limit of an over bn and I get a number, since it's diverge, it belongs down here. Don't I want that number to be any number in the universe, but not 0? Because if it is 0, I've screwed up somewhere, right? It's not going to work. So I'll try the limit as n tends to infinity of an over bn. It's going to be the limit as n tends to infinity of the original, that's this guy, divided by 1 over n to the half. So it's going to be the limit as n tends to infinity of the top fraction times the reciprocal. And I've just realized that I better do something. If I want to multiply 3 square root of n by n to the half, shouldn't I call that square root of n as well? Or call that n to the half? But whatever I do should use them in the same format. Are you okay with those two guys being 3n when you multiply them? Right, n to the half times n to the half is n to the 1. Right? Or square root of n times square root of n gets you n. Right? Whatever way you want to look at it, you still get an n, and 3n gets you 3n. And this one here, I could do a L'Hopital on it because it's so easy. It's 3. And so according to this one, the diverging version of the limit comparison test, is my ratio a number that's not 0? Yes, it is. And that means that it diverges. So the original series diverges by the limit comparison test. Are we good? Are we getting better? Every time you do it, you might be able to say, okay, I begin to see how you're approaching this question, what you're doing first, what you're doing next, and then how you're coming up with a conclusion. And it's based on if it converges, do this, and if it diverges, do that.
So I understand the algebra,
Mm-hmm. But
but I want to know, like, and I don't know if I should be asking this, because it's probably the worst question I could ask. a
no,
math
go for it.
professor.
Okay.
As an engineer, where do you
Mm.
use this?
I can't see a reason for an engineer to use these, John. I don't know of any situation where that would be a useful process. The closest I can get to series is when we do later on things called power series.
Fourier?
That's an example of a different kind of power series. That Fourier series use sines and cosines. We use powers of x, but it's the same family of math. In a power series, you might be able to solve, say, a differential equation by creating a series that behaves like the solution does, because you sometimes don't always get solutions. And so there's when you do DiffEq, well, I don't know if don't teach DiffEq, but if you do DiffEq 1 or DiffEq 2, you might be trying to solve a very simple differential equation, like find a function whose second derivative is equal to its first derivative plus x cubed, right? Something like that. And sometimes you get lucky and the solution is actually some function of x that you can get exactly. But a lot of the time what you can do, because you can't solve it that way, is that you build a series for your solution. You know, and they look like that. And those series generate things like that. And you want to know, is this series actually even usable? Because for certain values of x, you can plug it in here and the answer will converge to a number, which would mean that, yeah, I can use this solution when x is any number between 5 and -5, but I can't use it for anything bigger than that because the answer is divergent. If a series is divergent, it means the answer's infinity, which is probably not a good idea if you're an engineer to have that. But that's about the closest I could come up with why you would want to do these. In some situations, the solution to a differential equation is a series. And once you have a series, you might want to know for specific values of x. For instance, if I said x was 1, this would turn into that guy. Right, because 1 to the power of n is that. And does this converge, right? Could I use it when x is 1? Well, this one does converge because we could prove it. And that means that, okay, as long as x is 1, I know that this is going to work. Could I use it if it was -1? Could I use it if it was 10? And then you build up an interval of x's where a power series like this is going to converge and therefore usable.
Thank you.
Okay, but pure math wise, they're just fun. They're cool because they're cool. Now, here is question 16. And 16 and 17 are virtually the same, right? So I'm going to pick 17 because it's slightly harder. And this is, I believe, the first time we are going to do a limit comparison test to a geometric series. Okay, here goes. Only one of these two terms is going to stay alive. And the reason it's going to stay alive is that one of these two terms is bigger than the other once the n gets reasonably large. So which one do you think is going to be the biggest? 2n or 5 to the power of n when n is reasonably large? What do you think?
I gotta go with the 5 to the power of n.
Yeah, can you imagine 5 to the power of 10 is massive, right? And 2 times 10 is only 20, right? It's not that big. So in the same argument, could I also do 3 to the n on the bottom? Agreed? It's bigger than 2 times n. Now, we can simplify this down to look like that. Are you comfortable that 5 to the n over 3 to the n is also the same thing as 5/3 to the n? So far, so good? Now, do you recognize that this is a geometric series and that the R value is 5/3? What do you know about a geometric series whose common ratio is 5/3, which is bigger than 1? Converges or diverges? Geometric series, common ratio bigger than 1. Converge or diverge?
Diverges.
Correct. Isn't that kind of back to front for P series? For P series, don't you want P to be bigger than 1 to converge? For a geometric, don't you want R to be less than 1 to converge, right? It's almost like back to front. Okay, so we already know that this answer is going to be divergence, right? What we're going to do now is prove it. So, where's my guy? I threw him away? I hope not. Here we go. There's our guy. This fella here, right? We want to prove that the ratio AN over BN is a number that's not 0. So it's going to be the limit as n tends to infinity of AN over BN. So it's going to be the limit as n tends to infinity of the original function divided by this guy. But I'm actually going to use this version because it actually works better. I'm going to use that version. So it's going to be the limit as n tends to infinity of 2n plus 5 to the n over 2n plus 3 to the n times 3 to the n over 5 to n, right? Instead of dividing, you multiply by the reciprocal. And this now becomes 2n times this guy gets you 2n, 3 to the n's. If you multiply 5 to the n times 3 to the power of n, you're allowed to combine them into a single 5 times 3, 15 to the power of n. And then if you do the other guy, it's 2n times 5 to the n plus 15 to the n. Right, that guy times that guy. Okay, we are going to take this guy and find out what the limit as n tends to infinity. And this is not pretty. You could try L'Hopital. Don't. It doesn't go anywhere. What I am going to do
Can
is
you
divide.
factor at this point? Can you take a 3n and a no, right? 3n out the no, I guess not.
Well, you could factor, but I don't think it helps. What I'm going to do is divide the top and bottom by 15 to the n, which is essentially the biggest powers I could find. Let's see what we get. You're going to get the limit as n tends to infinity. This guy becomes 2n times 3n over that guy, which is 3/15 to the n, plus 1. And this guy gets you 2n And these two get you 5 over 15 to the power of n, add 1. And then you're going to have to trust me on this. If n goes to infinity, right, what will a fraction, 3/15, which is actually a fifth, what would a fifth to the power of n get you when n goes to infinity? And the answer is it would get you 0. And it would get to 0 quicker than this guy. So my argument is that you get 0 plus 1, 0 plus 1, which is 1. So I'm just doing brute force. I'm just saying that when you make n infinite, this entire expression gets killed because this guy gets to 0 so much quicker than that gets to infinity. And, oh, we got a limit that's not 0. So the original series converges. Sorry, diverges. Told you that one was ugly, and it truly is. But it diverges, and we've proved it. We're about 3 questions off finishing this. So if you can hang in for a few more questions, we'll be over the hump. Of course, the further down we go, they're going to make the math, the algebra, really weird. Okay, let's try that guy. Okay. You can only write a single power of n on the top. What will the square root of n plus 5 be written as if you do that? Only write it as a single power of n. What would you get?
Isn't it, is that n, square root of n
That's it.
times the square? No, it's not that.
No, that's it. Just the square root of n. Not anything more. Right? Basically getting rid of the 5. Because in the big scheme of things, isn't a billion and a billion and 5 not really math, right? It's still n. Now, on the bottom, that one we've done enough of to be, I think, pretty straightforward. The bottom is 2n squared. Now, if I call this guy 1/2 and I call this guy n squared, can you see where the 3/2 is coming from? Right, n to the half on top, n squared on the bottom, do a quick little division, you get this. And I don't like 2's, so I'm going to call it that guy. Okay, back to P series. This guy is a P series with P equals 3/2, which is greater than 1. Will that P series converge or diverge? P greater than 1. Converge or diverge?
Converges.
Agreed? Converges. Okay, let's finish this proof. The limit as n tends to infinity of the original divided by the comparison. The original is that guy over 2n squared plus n add 2. And the other one is that guy. So it's going to be the limit as n tends to infinity of the top fraction times the reciprocal. And I'm going to combine them before we do any more work. Well, that guy times 1's dead easy. You just get that guy. Now I have to figure out how to multiply this square root by this fractional power. Well, if you want to multiply a square root by anything, it's a good idea to have both of them as square roots. So I'm going to call this the square root of n cubed, which is the same thing as 3/2. So I will now have the square root of n cubed times that guy and n cubed times that guy. So that was a little bit of algebra to combine everything. Now we have two choices, L'Hopital or divide top and bottom by n squared. I'm not going to do L'Hopital, never do. Square roots don't play well with L'Hopital, don't do it. And I'm going to divide the top and bottom by n squared. But I'm not going to call this guy n squared, because if I want to take a square root and divide it by anything, I need to write it down as a square root. So I'm going to call it divide by the square root of n to the 4, right? It's the same value as n squared, but it is written in a format that allows it to work with this guy. So the top and bottom, although they're both n squared, are being written in a different format because of algebra. Divide that, you get 2. Divide that guy, you get 1 over n. And divide that guy, you get 2 over n squared. Divide that guy, and you get 1. Divide that guy, and you get 5 over n. Right, that's where we are now. At this point, you can brute force. 1 plus 5 over infinity. 2 plus 1 over infinity plus 2 over infinity squared. That's 0. Square root of 1 plus 0 gets you 1. 2 plus nothing plus some more nothings. The answer is a half. Is the limit not, right, 0? Correct. It's not 0. That means our guy, oops, was I looking at the wrong one? I think I was. Is our guy a limit that's not infinite? Yeah, it's not infinite as well, so that still works. So our series behaves like this one, so it converges. Okay, there's only one last one I want to do, and I'm going to give you a shot at doing it first before I do it. So this is a version of question 20. And I'll start it off for you, but it'll be your job to finish it. So it's the square root of that guy on the top, and it's an n cubed plus n squared on the bottom. So I'm going to take it as far as finding the comparison series. Biggest power on the bottom, n cubed. Can you help us out here? What would I use on the top? What should I write here?
Do you write n squared?
Okay. And n squared, for those who are not sure where you got it from, wasn't it the square root of n to the 4?
Yeah.
So that guy gets you 1 over n, right? Finish it off, get the limit. You got 2 minutes. John, I'm getting emails from you. Did obviously you got in, so did you get in?
Yeah, I got in, but I used the last link that you provided, and that link didn't get me in. So I used the one prior to the last link, and that one got me in.
Go figure.
So I was really confused, and I'm sorry for sending you so many emails, but I couldn't get
Uh, I have no idea what the previous link that did work or the previous link that didn't work is. But now you know whatever the right one is, just keep using it.
Roger that.
It was probably the link to the office hours that you sent after the one for the first time.
Oh yeah, that link was sent because the officer link no longer works. Yes. That's annoying, but evidently you only get so many officer.
Yeah, I probably didn't read the message. Obviously, from what she's saying, I didn't read the message. So
Well, I don't know how you possibly could get that wrong because I never make mistakes. That was a joke, but okay, let's get this show on the road since it's the last one. The original is this guy is AN, and the simplified version is this one, which is BN. Now we can see that this is a P series and that P equals 1, so I know it's going to diverge. So what that means is that we're now going to be doing the limit of this thing as it tends to infinity, and I think I'm going to do it underneath for space. So it's a square root of n to the 4 plus 9 over n cubed plus n squared, all divided by 1 over n. That in turn becomes the limit as n tends to infinity of n to the 4 plus 9 over n cubed plus n squared times n over 1. Now, since I need to combine these into a single expression, and this is a square root and this is not, then I have to do that little sneaky tricky calling n the square root of n squared. Now that means that we can now combine them inside the square root to get that. And on the bottom, you get that. Okay. The technique that I'm going to use is similar to the previous one. We are going to divide top and bottom by somebody. Right? And it's going to be a power of n. And it has to be the correct power of n. So what do we divide top and bottom by?
The square root of n to the 6.
And on the bottom?
N to the power 3.
Yeah. So what we now get is the limit as n tends to infinity. Each of these get divided by this fella, so you get the square root of 1 plus 9 over n to the 4. And this guy gets you 1 plus 1 over n. And then if you do brute force, you get the square root of 1 plus 9 over infinity to the 4. And on the bottom, 1 plus 1 over infinity. These two guys are 0. The whole answer is 1. If you diverge, is your limit a number that's not 0? Yes, my limit is a number that's not 0. So I can now say, so the series does this, and this guy diverges. So our series diverges by the limit comparison test. So before we go, and I'll be hanging about for homework questions and anything else, a couple of things I want to remind you of. Your grade letter should have been sent out. So you can have a look at that, see what you got. And your homework and your test, online test 7 should be visible so you can go in and look at it. One last thing is, if I find it, come on, stop hiding. Okay, you are hiding. Okay, I can do that. What in the heck are you doing? My computer is fighting me right now. That is not good. Okay, that's better. I'm almost ready. Just shrink this a little. Right, so I'm going to jump over and show you the homework for one last time. With the exception of question 1, have you noticed that all the answers just ask, for the most part, convergent or divergent? So it's either this one, or it's this one, or it's this one, oops, or it's this one. And it's very easy to cheat. Since there's 5 guesses, if you pick that one and it doesn't work, it's this one. I don't want you to, and I know the temptation is really strong for you to do that. Because if you go through this, you should be able to get 100% just by guessing right until you got the right one. You are going to get questions in the final, and in the final, I need to see all this working that we've been doing. If you've just been, I'll hit the first one, if it doesn't work, I'll hit the second one. When you get that question, I don't care if you tell me it converges and it's convergent, because if that's the only thing I see, you've proved nothing, right? You've just proved you were good at guessing. So bear that in mind. Secondly, when you're doing the online test.
I'll agree to that if you agree not to put one of these square root things on the final.
No, John, I'm not saying I will. I won't say I won't. You get. I've got such a bad memory. I'll forget this conversation anyway, so I might put one in anyway.
I mean, you could just give us the answers to the final as well.
Yeah, I could, but I would. That's wishful thinking, Colin. So, you know, bear that in mind. When you do your online test, you won't know if you're right or wrong. So you could get 50%, I guess, by being very lucky. Because in the online test, there isn't any opportunity to show working. But that just bad habit. So, you know, do it the right way and things will be better for you in the long run. And that is it. Thank you for hanging around and quite
Would you mind
subject.
taking a minute and just recapping all the test names that we have?
Oh, sure. Let's do that right now. That's easy. If you're not interested, you can leave right now. Otherwise, you can hang about while I do them in no particular order because I might forget some.
No, that's fine.
The first one is called the divergence test. And that's when you find the limit of the individual terms, and if they're not equal to 0, then the thing diverges. But that's all you can say. And then after that, we have a geometric series test.
I had a thought of on the divergence test. I found that I consistently mix it up with the sequences and series.
Yes, because the sequence, it will converge to 2, but in the series, if the sequence converges to 2, the series diverges, right? So they contradict each other at times. They're not really, but they sound like they are. The third test is called the P-series test. We have a test called telescoping series. We have an integral test. We have comparison test. And we have what we've just finished doing today, both of these actually, but this is what we did the second half. Limit comparison test. I don't think I missed any. So that is 7. We still got alternating series, ratio test, nth root test. So we still
Oh, there's
got a
harmonic
few more to
too.
come. Oh, the harmonic. I'm trying to think where the harmonic. Isn't the harmonic just a special case of the P series?
Oh, is it? Okay, cool.
Yeah, because the harmonic is just a P series P equals 1.